Okay, so another application of anti-differentiation is when you have a function, so you have a curve, so it's y in terms of x. The path of the curve is not a straight line. So according to the function that you have, it's a curvy path. Now, if you wanted to find the exact length of traveling along that curve, there is a formula to determine that length. Okay? So one way to do it is if you know the function, it's a rule given, it's y in terms of x, okay, and you want to find from x equals a to x equals b, you just apply this formula. So this is a formula that you need to know. Somehow that formula is not always on the formula sheet, so it's something that you need to kind of have that on the back of your mind. So it's integral. Just let me check if I'm still recording. Okay, so uh, it's the integral from a to b, and what you need to do is square root of 1 is the square plus, it's using Pythagoras, so just applying the formula, and it's dy over dx, which is that function that we differentiate, you square it, you add 1, and you do the square root. That will give you a new function in terms of x. That, from all the strategies that you have, you need to be able to anti-differentiate. Another notation, so instead of dy over dx, it's f prime of x, okay? Because you integrate from x equals a to x equals b, over that interval, boundaries included, we need to assume that f is differentiable, or it's the equivalent of saying that f prime, the derivative, is continuous. Okay? Alright, so example, find the length of the curve y equals x to the power 3 over 2. Now, good application. When you have a polynomial and the power is rational, always turn it into a fractional power. Otherwise, you're gonna have some difficulty to anti-differentiate. So it's from interval from 1 to 4. You look, it's a direct application of the formula. So that is your y. You differentiate, that gives you your derivative. Then for the length of the curve from 1 to 4, you apply strictly the formula, you substitute, you simplify. Now here we're trying to get rid of the fraction, so we have that integral, and it's a polynomial, but you're gonna have to use a you probably would use a chain rule to do that. If here they jump the gun, they go straight away by doing anti-differentiate that. All they did is they introduce the 1 over 27. It's probably better if you actually do a temporary substitution if you're not confident to do this. Okay, let me do that. Actually, I'm just gonna go and do that, because it's actually good to know. So let me do that. So here, I think you can still see the function. So let's say we okay, we have a half here, we have a half here. I want to go from that step down to that step. So I'm gonna just extract that integral from 1 to 4 of I do like to have the x in front, so I'm gonna write 9x plus 4. The square root is the power 1 over 2, and then it's dx. Okay? Now, the way you would usually do that is you do a substitution. U equals 9x plus 4. Okay? Du over dx gives you 9. Okay? And what you need to do is you go back to your integral. I'm going to call it integral here. It's going to be integral of so it's integral from 1 to 4. Now that's my x, and I'm going to leave the boundaries because I'm going to substitute back into x. I'm not going to leave it as a u, so it makes sure that it's going to match that actual answer here. Okay, so that 9x plus 4 is a u to the power of 1 over 2. That dx, it's coming from here, so it's dx, it's du over 9. Okay, now the 1 over 9 is the 9, they left it inside, so I'm going to do this. So I want to have the exact form with the 27 as a denominator here. Sorry, the 27 here. Okay, so I'm going to do 1 over like that. Now, u to the power of 1 over 2 du, it's a polynomial. To anti-differentiate, what you do is, to the power, you add 1. A half plus 1 is 3 over 2. So, by doing that, 3 over 2 means you need to factorize. So, the 1 over 9 doesn't change. But if you have a 3 over 2, you need to multiply by 2 over 3. Okay? And that's the u to the power of 3 over 2, like that. X is equal to 1, x is equal to 4. And now what I'm going to do with that u, because I left the boundaries as x, I'm going to substitute that u back to what I have here. So now my I is equal to 1 over 9, so I have 2/3 of 9x plus 4 to the power of 3 over 2 from 1 to 4. Okay, now I'm going to combine that 9 into here, inside the integrand, so that's 2 over 27, 9x plus 4 to the power of 3 over 2 from 1 to 4. So now we're back from here. Now we're back to this form over here. Okay. Now it's from 1 to 4. We substitute 1 and 4. So 1 over here in the negative part. The 4 is in the starting term. You do the difference. They expand the 1 over 2, and they get that answer for the length. Okay. Quickly, just double check that it's positive. Based on the formula, it's a square root of a square function. It's always going to be above the x-axis. You start from a value that is less, so 1 is less than 4. So yeah, that integral is always going to be positive. So quickly check, if you have the time, quickly check that it's positive. If it's negative, you made a mistake somewhere, probably here along the steps here when you anti-differentiate, and with the, you might have sometimes you make a minus here and you forget to have a bracket. Just the common mistakes that you can encounter. Okay? Alright. Next. Now, another way you can express that, so the first way is you have y as a function of x. So the coordinates of the point moving along the curve is xy. Another way you can express this is using parametric coordinates. With the parametric equations, each x and y coordinates are expressed as two functions in terms of a third parameter, which is we call it t. It's a variable. It's a time variable. Point P has the respective coordinates. It represents a curve. Now, the interval you're looking at is t again. It's time, so it's from a starting time to an end time. When you apply to find the length of the curve, the function you apply is from t equals a to t equals b. So it's in terms of t. And what you do is square root of the sum of the square of the derivatives. So what you need to do is differentiate x and y in terms of t, and recreate a new function which is a sum of the squares and then you square root. Okay? Along that interval, f and g have to be differentiable, or the two derivatives in terms of t have to be continuous. So example, you have the two parametric equation for the coordinates. You go from 0 to 2 pi. By the way, it's an equation of a circle. So if you have an equation of a circle, 0 to 2 pi represents a full revolution. And what's the radius here, by the way, of that circle? If you know the radius, so tell me what the radius, and then once you know the radius, how do you can estimate, without using that method, the length of the curve around the circle? Oh, I need to, Minerva is here. Let me update the ball. Alright, no one? Okay, so when you have x and y, the curve is a circle of radius 1. Okay, so if your radius is 1, do remember the length of the curve on a circle is the same as what you call the circumference. Okay, so it's going to be 2 pi the rate r, or the radius, which is 1. So if you do your calculation correctly using integrals, your answer needs to be 2 pi. Okay, so we have x and y. You differentiate those two, so we get dx over dt, dy over dt. Do remember, for the derivative of cos it's negative sign, for sine it's cos. Then we have our two derivatives, we square them and we add them together, so sine squared plus cos squared, that equals 1. We square root that, still gonna be 1. The antiderivative of 1 in terms of t is going to be a linear function t, okay, from 0 to 2 pi, so that will give you 2 pi minus 0, which simplifies to 2 pi. And that will be the length along a circle after a full complete revolution. And that's it for chapter 8 and 8e. Stop my recording.